So welcome to this first module about neural dynamics, properly speaking. I want to connect first to what I did in the Breitenberg lecture to talk about activation, where that comes from. So there, remember I talked about activation that ultimately comes from the sensory surface. So sensors that in some sense are transducers from something physical and intensity into something neural, and we'll call that activation. I'll come back to different meanings of activation in a moment. And so it's that activation that we will now be talking about when we talk about neurodynamics. And then at the other end, we will I consider that ultimately some motor system transduces an activation back into something physical, into some physical action. So somewhere in between is the nervous system that's in terms of this activation variable. Now, activation, the way we use it is the way it is used in connectionism and a couple of other sort of neurally inspired models of cognition. For instance, some of you might be familiar with ACT-R or SOAR or the cognitive architectures that use an activation concept that's sort of like that. It's an abstraction of the state of neurons, the physical state of neurons that contributes to their function. So in one way, with respect to the underlying neurophysics, you could think of that being reflective of the membrane potential of neurons that determines how close they are to transmitting their state to downstream neurons, and that transmission takes place through synapses, as I mentioned in my introductory lecture. And the spiking threshold is really what makes neurons then have an effect on downstream neurons. And at the level of abstraction we're using in these lectures, we're capturing that effect of the spike formation by just a sigmoid function. So it's a function that's monotonically increasing, goes to zero for sufficiently low levels of activation, and goes to some constant, which we defined conventionally to be 1 for sufficiently large levels of activation. And so then it transitions, it's a monotonic function that transitions in some way. The slope, how steep that transition is, essentially fixes what the units of activation are, right? If we don't have any other measure of the effect of activation, then all that we can say is if you have a certain steepness of this sigmoid, then that defines the range over which there is significant change in the output behavior of neurons. So the steepness as such doesn't really mean anything. So ultimately, the units of activation are only fixed when you connect these systems ultimately to some motor system, and then you really affect some rate, something that again has physical meaning that translates into some motor activity. So that's an abstraction. It's an abstraction of something that's really ultimately physics. It's the physiology of these ion-filled membranes. I have offered, I'm not sure I actually articulated that, but I'm happy to give a tutorial lecture about that underlying neurophysics, the spiking mechanism, Hodgkin-Huxley, a little bit synaptic things. Maybe at the end of the lecture, you can voice your interest or lack of interest in such a lecture. So for now, I'll just draw the analogy to show you how the language, the abstract language we'll be using is continuous with that sort of phenomenology at the physical level of neurons. In the rest of the lecture, we'll not really think of concrete neurons, and it's not really necessary that the models that we'll be looking at can be interpreted as models of individual neurons. And in fact, I'll point out in a couple of cases that it's not the case, that we're really looking at a population level that is even abstracting in an important way from individual neurons. But to understand where things come from, that these equations don't fall from heaven, let me give you a little bit of intuition from that. So here's a simple caricature of a neuron that has an axon that's this protrusion from the cell. Inside the cell are different mixes of ionic liquids. So the membrane isolates that liquid from the outside, and as a result, there is a potential difference between inside and outside the cell through mechanisms I've I can then review. And the membrane has of active electrical properties. So for instance, if you insert a electrical impulse, like a current, at one point into this membrane, you can measure at another point the intramembrane or intracell electrical potential is generally negative compared to the surround. And when you put a little current in here, you will see a rise of potential followed by a relaxation back to the original resting potential on a time scale of milliseconds. So typical exponential relaxation that you observe has a time scale of 10 milliseconds. If you vary the amplitude of this current, the amplitude of this electrical excursion varies. The spiking mechanism is the thing that we're not modeling. That is, if a threshold is reached, there is a potential, transient potential that the amplitude of which no longer depends on the amplitude of the input. And again, that's something I can review there. So from this time course, we can sort of get a sense for the time on which electrical potential inside cells evolve. So 10 milliseconds sort of typical time scale of that. So it's relatively slow if you think that neurons, that nervous systems can evolve, like you can make a reaction time of 150 milliseconds, let's say, then that's not really very removed from that, right? For instance, if you compare that to a digital computer that you're all familiar with, some of those have gigahertz cycle times. So that's 9 orders of magnitude from the times on which, let's say, a computer is controlling a car or controlling a robot. So it's much faster than the physical times we're dealing with. While here, the physical mechanical times and the electrical times are quite similar. That's an interesting challenge for computational neuroscience. So the mathematical description of the evolution of a membrane dynamic, membrane potential as a function of inputs is sort of this form. This is the form we'll be using. It's the rate of change of that electrical potential has a relaxation behavior, this minus u. You've studied that in the exercise, right? That makes exponential time courses. And the coefficient here in front of that, or put here on the left as a tau, determines the time scale of that exponential relaxation. And that time scale is about 10 milliseconds for the membranes. And that's what we will be using as the basis for our modeling at the population level. And I'll not explain exactly how you get from this spiking level to the macroscopic level. There are a few cases where people have made mathematical derivations of population level descriptions, making some assumptions about the underlying populations. Assumptions that are not really actually quite realistic under real circumstances. So we can say that the equations we'll be using are derived from that. They are structurally similar to the equations we see at the individual levels, and they're phenomenologically appropriate. And I'll only provide limited evidence for that, but I'll provide some. That is, you can use these equations to fit the evolution in time of populations of neurons, the activation population of neurons, the firing of those. And in that sense, they are good neural models. At the level of neurophysics, when you drive neurons with the different currents, so that this activation variable in this picture is at different levels of activation, when you're above threshold, that will being at different levels of activation is reflected in the rate of spiking. So these neurons make these action potentials, and there will be a large distance between the individual action potentials when activation is not much above threshold, and the rest, the activation that results from the input and the this is the membrane dynamics, the intrinsic properties, and together with the input, they determine that firing rate. And so you will have higher firing rates when there is more input. So that's not what we'll be modeling. We will be characterizing these different situations by saying activation is at a different level, and a different level in the above threshold regimes, or at a positive rate of activation, which is not really then anymore really the membrane potential. So that's the macroscopic description we'll be using. Again, will be a whole topic to link that to the spiking level. So let's go into this in a little bit more detail, try to understand this here. Yeah, there's a question. No. So this is a dynamical system. Those of you who just learned that in the tutorial will recognize that it is against the idea that you have the rate of change of something as a function of that something. Here the something is activation, which I denote here by U. Whenever that's the case, it's a dynamical system, right? That function f in this particular case is a linear function with a negative slope. And you already know from the tutorial that leads to stable states, and these membranes do have stable states. Physically brought about by particular processes that I didn't explain. Conventionally, what we do is we say that the sigmoid is centered on 0. So that's no longer, membrane potentials are actually tend to be negative at the resting state, but we just take 0 to be the threshold. The firing threshold is really below 0. But we're not physical here, it's more abstract. So to make sure that the rest, without any inputs, activation, the attractor for activation is at a negative level, we add a constant that is negative, this constant h, by convention. So obviously add a negative number rather than subtract a positive number. I don't know why. That's just, everyone does that, so we're following convention here. So h, the resting level, is a negative number, so that the sigmoid will only start acting on neurons that are not at the resting state, they are beyond the resting state. We call this attractor resting state because it arises when there are no additional inputs. So there's nothing here on the right-hand side except for this constant h. So that the 0 crossing of this negative line is in a stable fixed point. An attractor is what you went through in your first exercise. I argued for that in more abstract examples. You have negative values below this resting level, positive rate of change, so you will be increasing. Above this level, I have negative rates of change, you will be decreasing, so you'll be converging to that state. So I think that's all clear to you in the meantime, I hope. So we will always be thinking in this whole course about attractors, sometimes also repellers, and their stability. In many cases, because we will be looking at cases where the system is in or close to an attractor. But there's also a more general idea behind that I think Sophie in her tutorial sketched a little bit, that the attractor solutions really characterize the dynamic behavior for all solutions. So all solutions would arise, for instance, from different initial conditions. So here I started, these different colors are starting at different initial levels of activation, maybe from previous activation patterns that you had due to previous inputs. And then you would predict, and you study that in the exercise, that they all converge to the same stable state, the resting state in this case, the attractor. In fact, you could say on which time scale do they do that? The time it takes to reduce the initial distance to about a third, or 1/e, 1/2.7 of the that initial distance, that will be here. That is this factor tau, the time scale here. If I use a negative loop of unity, then this tau alone determines that relaxation time. And it doesn't depend on how far you initially are. It's always the same percent change that takes the same amount of time. So you see, this is the change from here to this level, right? About a third, that's where the tau is. So this a survey of the behavior of all possible solutions is called the flow. I think Sophie defined that very briefly. And in many cases, you can say that the attractor solutions characterize the flow. So knowing the attractors, knowing actually more precisely their basin of attraction, you can say what the overall flow is. So what qualitatively, what different kinds of outcomes could you have? And that's why the attractor solutions are so powerful. They tell us really about the qualitative dynamics, about what kind of categories of solutions there are. So in this picture, the input is just a contribution to the rate of change. So it's different from what I mentioned in the introductory lecture, that in the feed-forward connections picture, it's the output is a function of the inputs. Here, the output is the sigmoided activation that evolves from the differential equation. The inputs are actually, in a sense, generalized forces of the equation. The right-hand side of the equation means it's something that induces a rate of change, and that would be something like, in the metaphor, would be like a force if this was a physical dynamics of some particle moving in a force field. So we'll consider these terms here added on the right-hand side to be inputs. If it's an external input that arises, let's say, from the sensory surface or from some other neurons, it will not depend on this neural activation. So it's an additive term that doesn't depend on you. If it doesn't depend on you, it means it's constant along the u-axis. So you can think of this contribution as a constant, that you could plot here as a horizontal line. If you have this minus u term here, the gray line would be this minus u plus h, the resting level thing, then a constant that you add to that, that means you shift the whole thing up. Like this arrow here would be the amount that you add at every location of u is constant. So that would just shift that line up to the line that's drawn here in black. That's what an input that is additive from the outside means dynamically. Now, if it's shifting that up, we would call that a excitatory input. It creates a positive rate of change. If it would be shifted down, which we'll see later, we'll call that an inhibitory input that would tend to reduce the rate of change. And the meaning, why does the rate of change indicate whether it's excitatory or inhibitory? Well, when you shift this up, then the attractor shifts to the right. And here in this case, it shifted actually into the positive range of u. So if you were to look at time courses, you would actually get the sigmoid to respond and become non-zero. So you recognize that the fixed point shifted to the right because you're adding input and shifting the curve up. And what makes the system to actually go to this attractor is, in a sense, the minus u term, right? It's the intrinsic dynamics of the membrane, if you wish. That makes that if you were sitting, let's say, initially here, that now you have a positive rate of change and you go here, that's from the minus u. Well, that's minus u term is not a term that you could compare to, excitatory inputs or inhibitory inputs. It changes sign actually as you change the sign of u. So it really sets up the intrinsic dynamics. The intrinsic stability gives this time scale. And by physically in the membrane, it really comes from the membrane properties. It doesn't come from the inputs that would be mediated by synapses and postsynaptic potentials from the synapses. So in that sense, what happens in the time course is that you're tracking this change of the attractor because of the stability properties of the attractor, and that amounts to something like low-pass filtering. So for instance, here in this simulation, I made the input jump to a new state, and then the system was moving from the resting states to that new attractor in a way that is not jumping, is moving with that exponential relaxation that is characterized by the timescale tau. The sigmoidal activity is a convolution of, or a concatenation of that kind of low-pass filtering, that sort of smoothed tracking the input, and the sigmoid function that makes that there where the activity crosses zero, the sigmoidal response stars, and then it saturates at some point. Again, I'm unfortunately always using sometimes sigma, sometimes g in the book. We always use g because sigma was used in other contexts, but it's more conventional in the literature to designate the sigmoid by that letter sigma. I'm not totally consistent with that. It's a bit unfortunate that we had this conflict. I actually like sigma better, so sometimes I'm using sigma when there's no risk of confusing it with, for instance, the widths of some Gaussians. We'll also use sigma. So up to this point, the dynamics as compared to an input-output system are really just doing low pass filtering, right? In an input-output picture, what you would get is that U is directly a function of its input. And so if the input is time varying, U is exactly the same time course as that input, maybe offset by any other inputs and maybe with a sigmoid in between, but no difference in the time course. And all the dynamics does is low pass filtering, meaning it makes sharp changes in time a little slower. And it's a so-called exponential filter characterized by that time scale. That's not really the most important aspect of dynamics, but it's the first thing that actually happens in the dynamical system. We'll see more happening in a moment. I had planned to simulate that on in MATLAB. I wonder if that's maybe too trivial. You did go through a simulator like that, yeah. So what I actually want to do is go to our web page, and I'm not sure you saw this page before, the dynamicfieldtheory.org page, which I reference on the course, the web page of the course, where you actually have a nice live simulator here right on the title page, which is fun to look at. But here I'm referring to a specific neural live simulator that you have here under live simulations 2 neurons. And that simulates 2 neurons, as the simulator says. And we just need 1 neuron now. So here is the activation dynamics of 1 neuron, U1 as a function of U1. This is activation. This is the rate of change. Negative slope. Here's the zero crossing. This dot here is the attractor. And the system is actually sitting in that attractor right now. Here's a running time course of that. The activation plotted here on the y-axis, and current time is always a 0, and see the recent past. This is the 2 neurons plotted against each other. This is a second neuron that has the same dynamics, and we'll use that a little later today to look at 2 coupled neurons. So when you have a single neuron, you can change a couple of parameters. So for instance, you can add input, and then you see I'm lifting this up or down, and you see how it tracks it. And you can actually see with the slider, I'm changing the input not instantaneously, but as fast as I can move that slider, and you see the low pass filtering that the system just tracks that, but has this characteristic time delay. That's what you can say so far. And here in the picture here on the left, you see how the line seems to be shifting up and down as I move input, and that means that the attractor shifts left and right, and that's how the track comes apart. You can really literally see the system running down this line. So it's the minus U term that drives the system into the attractor and away from the attractor. Okay, we'll be coming back to that in a minute. Good. So that's the base function of a single neuron just reacting to input. Now we'll be interested in neural networks that are not just receiving input, but that are contain recurrent elements. And the simplest recurrent element we look at is a single unit. Is actually, we will later see a small population we're modeling here, but mathematically speaking, it's a single unit, and that makes a recurrent loop by the output of that neuron serving also as input. So this output is provided as input. Mathematically speaking, this would mean that we have this neurodynamics with some external input will vary, and there's another source of input that now does depend on U, and it depends on the sigmoid of U, only the output, the sigmoidal activation with some constant C. We could think of that as self-excitation. There are actually literally neurons like that in the nervous system, especially actually in some invertebrates. We find that all over the place. But again, we'll see later that we'll really talk about populations there where the excitation is among different units in both directions, and then together as a population, they have this property, not necessarily that it's the same neuron that makes with its axon a synapse on its own dendritic tree, even though that does also happen. Now here, mathematically, what does that lead to? We have a minus U term, right? That's the same resting level, the first term here. This is with 0 external is input. So S is 0 at the moment. And the sigmoid is a function, rate of change is additive to the rate of change, right? Rate of change as a function of U. The sigmoid will be a function that is centered here the turning point is at 0, then saturates to 1 and saturates to 0. So if you add these two curves, I'm assuming that I put the C already here into this plot, then what you will get is something that here in this domain behaves just like the minus U term. So here it should be behaving just like this. And then actually, it's funny, the scale is a bit different. This here should be lined up. Just notice that they're not actually nicely lined up. And then here on the right somewhere, you will be just adding this constant to the minus U term. So it will be like the minus U function, but shifted up. That's this part of the plot. And in between here, excuse me, where the sigmoid interpolates between two limit cases, well, you would interpolate between this minus U and the shifted minus U, right? Something like that. So this is a function that is no longer linear as a function of U, right? It's a nonlinear curve with the sigmoid function being the source of the nonlinearity. Now that nonlinearity here is, in the case I was plotting here, isn't really making a qualitative difference because you still have the property that everywhere on the right, U dot is negative, so you will always be decreasing until you converge here to the resting level. And everywhere to the left of this, it's positive. So the qualitative dynamics is not really different. Again, qualitative dynamics being the flow as an ensemble of all initial conditions, they're just deformed a little bit. They will be slowing down here a little bit, but qualitatively they all have the same property. They end in the attractor. But there are conditions now when we look at different inputs where that's no longer the case. So here I'm plotting with this gray shading different copies of that dynamics at different levels of external input S that I'm assuming is constant now in these plots. So very little S and then increasing input strength S, some constant added. So you see that there are intermediate ranges where there is a fixed point here. Let's say this one here is a fixed point with a negative slope and an attractor, and then there is a fixed point with a positive slope, which is a repeller, and another fixed point with a negative slope, which is another attractor. Let's look inside into this intermediate regime. This is a regime we would call as dynamicist bistable, and you did look in the tutorial at systems like that. Bistable means really there are two stable states, these two, this one and that one. One could call this the on state because the activation is positive, so the sigmoid would return a non-zero value. This one would be the off state because the sigmoid would be returning 0, if this is scaled correctly. And this is separated by this other fixed point that is a repeller. And so the qualitative dynamics is that any time any initial condition above 0 would converge to this fixed point, and you see that here in the simulation set of simulations, and any initial condition to the left of this repeller would be converging to this fixed point. These are these simulations started here in red, where the initial state was smaller than 0. I should have said U. It's actually true across time, but I meant really U at the initial time is smaller than 0. So this is called bistable. We refer to that in the Brightberg vehicle case as a possibility of how to model these mental decisions. So we decide to go to this or to that state based on the initial condition here of activation, not of that indirectly. Now you get into this bistable regime, or actually you have one way of getting out of that bistable regime in an instability. So if we think of this bistable regime we just looked at, and we keep adding input, then this curve would be lifted up, and at some point it would be just tangent here, and then at the next moment in time, or next level of input, it would not have any intersection with the U-axis anymore, and there would be no fixed point in this region here. There's actually at all times this other fixed point, the on state, that is just shifted further to the right. So what happens here is a bifurcation. You saw bifurcations in Sophie's lecture. This is actually a tangent bifurcation locally. If you just look around that picture, she went through the normal form, which is the generic equation just local to the bifurcation, infinitesimal around the bifurcation, where you don't take into account that something happens very far from the state. And so what happens here is exactly what you studied there, that an attractor and a repeller collide and then dissolve as you increase stimulus strength. That will be the bifurcation parameter. Plotted here as a bifurcation plot, the fixed point as a function of the bifurcation parameter, the unstable and the stable branch collide and then annihilate the step. We call this the detection instability, and it plays a very important role in dynamical field theory. Almost everything we do is based on that instability. And I'll highlight a few of these points. Detection, the name comes from the idea that this neuron U would represent something by virtue of how it's connected to input, would represent whatever the source of that input is. And this is where it makes the detection decision, in the sense that if it was initially in the off state because it had not yet detected anything, through this instability, it switches into the on state. And therefore now signals to its downstream neurons through its sigmoid function that now whatever it stands for has been detected, is now active. It's now an active state for that. This detection is stabilized. So even if the input is then weakened after you made that decision, it will stay with that decision. So it will still signal that it has detected whatever it was. So if you recognize that the instability happens once the input strength is above the line, the level that's corresponding to this line, then you see that if you go below that line, you still have an attractor here. So you would stay in that activated state. That would mean that you made the regime monostable at the bifurcation. That's when this is gone, monostable, because there is this other attractor here on the right. And then you can return into the bistable regime, this intermediate one, or this one here, but you will stay in that attractor, the on attractor. There is also the reverse instability happening here on the right if you lower input strength, where you're going from having the attractor for the activated state, this other attractor and the repeller, and then they collide. If you pull this down, they collide here, and then when you go beyond that, this local attractor is gone, so there will be a small input strength. And then the fact that there's some other attractor around, again, is not a local property. That's a property of the global equation, and then you would be switching to that off state. So it's quite obvious why we call this reverse detection instability, because this would be the point where you're reversing that decision that you have detected something, and it would happen at lower levels of input. You see, this is a lower version of the curve at which the other one occurs, the detection. It occurs at a higher level of input than this one here. In between is the bistable regime, where you base your state of detection or non-detection on your recent history. If recently you were above, then you will stay above. If recently you were below, you stay below. So one reason why this is such a significant instability for us is that it essentially transforms continuous time courses into discrete time courses. So underlying this picture is an input that would be increased linearly in time. So make an S of t that increases from a low level to a high level as a linear function of time, just a knob that you turn in a graded form. So that's the most continuous form, like linear in time. And you see that the resulting activation level is a nonlinear function of time. It would stay below 0, and then at the detection instability, it switches to this positive level activation. It keeps rising if you add more input, but there's clearly a particular event where there is a qualitative change, where the system really switches from off to on. And actually here, for the other curve, I let time run backwards or decrease input as a function of time. And then actually at a different level, at a different moment in time, which corresponds to a different level of input, there would be the opposite switch from the on to the off state. So we'll see this time and again, and let's go through the whole lecture, that through instabilities like that, and the detection instability will be the most important one of those, events occur at discrete moments in time, even as the whole dynamical system evolves continuously in time from a mathematical point of view, and its input may evolve continuously in time. For instance, as an agent driven by these neural dynamics behaves and in the environment things change, there would be events when one of those instabilities occurs when the system changes state in a macroscopic way. And that's how sequences of states come about in our agents, but also in mental processes. We'll come to that in the second part of the course in quite advanced form. So this is delivered by a single neuron with self-excitation, standing for a single population that has mutual local excitatory coupling. So if I go back to this simulator on the web page, I can model this because I have a button here that controls the amount of self-excitation. So this is the C, the coefficient in front of that recurrent loop, currently 0, so no self-excitation. If I make it different from 0, let's say, I don't know, like 4, then you see that here, you see the sigmoid function brings about that centered around 0 activation. You have this transition. So this shift here from the hypothetical shift from the extension of this line up to this line, that will be the C that I'm controlling here through this connection strength. No, sorry, here, the self-excitation connection strength. As you see, nothing happened while the system was sitting here. So if I push the system through that reverse detection instability, that's where the other attractor comes about, right? Now the system is bistable, has this on attractor, but if I'm starting it in the off state, nothing happens. That's why I said the reverse detection stability is not where the decision arises to have an input. That actually is an instability of the resting state. So let's not go through these extreme values here. And now I want to vary input strength. And I can do that by moving this button. See this tracking here, this input. And again, nothing is changed while I have this attractor. So you see now the input alone is enough to induce a new attractor here and a repeller, but it doesn't affect the current state because I'm still in this off state. So only when this off state becomes unstable as it collides with this repeller, happening just about here, and there it goes. So it takes a little while, just at the bistability. Now it's in this on attractor, and now let's stay there. So if I weaken the input again into this middle regime, so it depends a little bit on input. It will track that input, but it will qualitatively stay above 0, so sigma returns a non-zero value. Truly bistable. And then on the other hand, if I go too low, these two collide, and then the system goes back to the off state. So that's the instability. So we maybe articulate this a little bit more so that we can see it better with the naked eye. So here I'm in the middle of that bistable regime. Now in this simulator, I actually have noise, which is a random contribution to the rate of change. Partial white noise. So at every moment in time, it's a new contribution. You see here, I actually did see spontaneous switching to the on state, but it's a lot of noise. You need a lot of noise to bring that about. We will see later in the field case that that's not realistic. When you have more realistic levels of noise, like these, it is exceedingly unlikely to ever get noise that kicks you above that repeller to get into the other regime. The only way that you're going to have a chance to do that is if you're very close to the instability. So for instance, if I'm going here, close to the instability, now this level of noise might be enough. And so even here, maybe not enough for that to happen. Just a little bit more. And now it switches. And the same will happen if I do that in the reverse. And so a general message from this very trivial example is that stochasticity that comes, where you get responses that don't depend deterministically on the current state and inputs that are different when you look at behavior from trial to trial, which is ultimately the source of free will, if you wish, the capacity to decide differently, given that everything else is the same. That is likely always, the account is caused by some non-deterministic processes, which could be noise, modeled by noise. And these processes will only have that chance to bring about qualitative change when you're close to an instability. So the instabilities are also really important in that respect, in bringing about unpredictable behavior. So the capacity to translate or to amplify a small neural phenomenon, neural noise, into a macroscopic change of behavior that occurs in an instability. It doesn't occur in general. If it were to occur in general, as it does happen here in the simulation, if I just make noise large enough. Now that's a case where the system is entirely stochastic, so it doesn't actually have any continuity. The dynamics can be neglected under these circumstances. It's all about noise. So so that's not the answer, right? That's not how stochastic decision making looks like. Stochastic decision making is the amplification of noise into a then stable macroscopic change. Get a lot of mileage of this scenario. Okay, that's the self-excitatory neuron. Any questions up to this point? Not. So then we'll be looking at two nodes. That's the most complex we'll be getting for today. It's a neural network that has two units that inhibit each other. I'm using here this notation sometimes used in neural modeling, where a synapse sort of is indicated by a circle is inhibitory. When it's just making a straight arrow, then it is excitatory. So looking at two neural activation variables that inhibit each other, rather than at two units that excite each other, because the case where they excite each other isn't really qualitatively different from what I just showed. If you have a single self-excited neuron, that's the same qualitative dynamics as two units that excite each other. You could maybe intuit that if they excite each other, then the ensemble will have the same kind of properties. If they excite each other enough, if it's in both directions, then they will show the self-excitatory loop that will stabilize the onset, make that kind of bistability. So to get some qualitatively different regime, I'm looking at the case where they inhibit each other. So inhibit each other means that, for instance, neuron number 2 shows up in the equation for neuron number 1 with a negative impact, so negative change of the rate of change, negative contribution to the rate of change. Assuming that this C12 is a positive number, then minus just as its negative contribution, and vice versa. U1 shows up in the equation for U2 with that negative coefficient. That will be the synaptic strength that's negative. In the nervous system, these are actually special kind of neurons that make negative synapses. They would be inhibitory neurons, and we'll get to that later in the course, that we'll actually have to distinguish between neurons of different types. But for now, we just assume neurons can make synapses that are positive or negative. So when you have that kind of connection, we actually talk about coupling rather than the generic connectivity. And coupling really refers to one kind of neuron affecting another kind of neuron, rather than, in fact here, reciprocally, rather than the connectivity coming from sensory surface in a unidirectional way. But it's not a rigorous difference. It's just that dynamicists tend to call certain kind of connections coupling. It's the mathematical concept that coupling really just means mathematically that in a dynamical system, you have a particular variable. When the rate of change of that variable depends on the other variables, and you say the variables are coupled. This is one direction of coupling. This would be the other direction of coupling. If you have both, you would call that mutual coupling. Doesn't have to be symmetrical. This doesn't, these coefficients don't have to be the same, but it's in both directions, non-zero. So some of you might know that's how we talk about dynamical systems in physics, where one particle influences the evolution of another particle. Now we say they are coupled. And if this goes in both directions, then they are bidirectionally or mutually coupled. So in neural networks, it's a form of recurrency. You could see this here in this graph, that you could say, well, this neuron, affects that neuron, and that neuron affects this neuron, and so you have a loop in this, and that's what we call recurrency, right? It's a form of loopiness. And the previous plot, the loop was just within one single neuron. So it's a little more complicated to get a actual impression of the qualitative dynamics of this system. I'm suggesting here one way to think about it, where we're sort of making case distinctions. It's complicated because we have four things to keep track of, right? We have the level of activation of U1, the level of activation of U2, and the rate of change of both of those variables. So if we were to plot the rate of change of the two variables against the two variables, it would be a four-dimensional plot, which is difficult to visualize and doesn't scale very well. So instead, what I'm doing is I'm plotting these individually. So even though the rate of change of U1 depends on both U1 and U2, I'm plotting these as two separate plots because I can't combine them really in this way. And the way I can keep track of the second variable is by making assumptions always about the second variable. So for instance, here I'm assuming that initially U2 has been activated in some way to a positive level of input. So that will turn out to be, for instance, true when this is the equation for U2. So if U2 is positive, that would mean that you really have that negative contribution, and I'm assuming it's positive enough so that the sigmoid here returns some constant value, let's say. So that would mean that the curve for U1, so even if there's some input to U1, curve to U1 is suppressed, and I'm assuming it's suppressed enough so that the attractor that was here at positive levels of U1 are now shifted to negative levels of U1. So this is mathematically the equation for the fixed point, and that would have to be negative. And if that's the case, then U1 will be negative. Its sigmoid returns a value close to 0, and therefore it will not contribute to this dynamics. And therefore, under these stimulus conditions, I would have an attractor in the positive range. And so then what I'm saying is it's a self-consistent assumption. If I make the assumption U2 is positive, then tracking this through the two equations, I find that that's consistent. You get a positive U2 if U1 in fact is suppressed. So that suggests that a solution to this equation under the appropriate parameter conditions that these assumptions reflect could have a state where one of these two neurons is activated, that would be U2, and the other neuron is deactivated, so it's at a negative resting level. And there's nothing in this argument that depends on U1 versus U2. So you could say, by the same logic, the opposite assumption should also be true. If U1 is activated, U2 will be disactivated. So there are two possible states. U1 wins the competition, or U2 wins the competition. This negative inhibitory influence, in fact, could be viewed as a form of inhibition, because if one of those variables is positive, it will tend to make it less likely that the other one is positive, because it adds a negative rate of change to that. Could say that's competitive coupling, a form of competition. Yeah. So which of these two cases would be typically observed, or why would U2 be positive and then U1 negative? One could say generically this happens in that this unit became positive before this unit became positive. Let's say they're both at resting level, then you get some inputs. And if U2 starts to be positive before U1 starts to be positive, then U2 can start to have an inhibitory influence on U1, but not vice versa at that moment in time. When it has an inhibitory influence on U1, U1 never gets a chance to get positive, and therefore never gets a chance to suppress U2. And then the small timing difference is translated into a competitive difference, and U1 will have won. And that is actually the general way of how competitive interaction in neurodynamics works that goes all the way into selection, which we'll get later. And, as you know, some neural networks will make categorization decisions, get some input, then decide this is a car or this is a cup and so on. These kind of decisions are deep down really caused by those neurons that stand for one of those concepts reaching positive levels of excitation a little earlier than the other ones, and that makes them suppress the other ones through inhibitory coupling before the other ones have a chance to suppress in the reverse direction. This time advantage comes from an input advantage. Right here in this example, it will be really the raw input strength. If I give a larger input to U2, then that will drive the U2 above threshold earlier than U1. But in general, of course, if you think of the neural network, it will be not just some raw input, it will be the question of how well the synaptic connectivity of one pattern, one set of neurons matches the current input. And when it matches the effective input to that population of neurons will be high. Well, if it doesn't match very well, it would be low. And this notion of matching I haven't really explained here, but for those of you who've taken courses in neural networks, you will understand that that is really what the synaptic connectivity vector, if you want, all the connectivities to all the possible inputs make, that if they match the input, they will provide effectively a lot of coupling. The neurons where it matches will respond strongly to that input. So good match translates into input advantage, translates into time advantage, and that translates into competitive advantage. So that's how selection really happens in these neural networks. So this is the simplest case of selection, right? I want to briefly show you another picture, mathematical picture of how to think about that, really more to illustrate the idea of a vector field and to make it intuitive. Because that's a very general picture that we can use actually mentally in a lot of other cases too. So mathematically speaking, I could think of these two coupled neurons as erecting a vector field. So here I'm plotting one of the single activation variable, the plot we always looked at, and these little arrows I used to plot along the horizontal axis could be interpreted as a vector field. So each is a vector that is one-dimensional here, so it just points along this axis. Its direction is determined by the sign of the rate of change, and its length reflects the rate of change. So for instance, you have a negative rate of change, so it points to the left, and it's a long vector because we have a large rate of change. And now here it points to the right, and large value because it's very large. Here's a smaller value. So you could say that this rate of change defines a vector. The direction is the direction of change, and the length is the rate of that change of the same dimensionality as the variable here along the u-axis. And that generalizes to any number of dimensions. So you have two neurons. You could think of any level of activation of these two neurons gives rise to a vector that's a rate of change of these two neurons. So it's a vector in this same dimension, pointing in a direction in the space u1 to u2. The length of that vector will reflect the total speed, how the rate of change along the two axes. So always be the horizontal component would be the rate of change along u1. The vertical component will be the rate of change along u2. And so with the same sign convention, pointing in downwards if it's a negative rate of change, and upwards if it's a positive rate of change, and to the right versus to the left. So this is the superposition of the two vector fields for the two components when these two components are actually uncoupled. This is the vector field in the absence of input without coupling. So what you can see is you go along this line where the vector field for U2 is 0. Then you see here the long vectors that are pointing here, and then the short vectors that point to the left becoming longer. So that's just this vector field reproduced. And similarly, along this axis, you're having that same vector field just plotted in the vertical. And everywhere else, you're just superposing these two things. So see, the horizontal component is always the same as here, and the vertical component is always the same as there. So this is actually an uncoupled vector field. It's maybe not always obvious when you look at it. You just have to sort of look at if the vertical contribution, you can see this here in this bottom line, the vertical contribution should be independent of where you're along the horizontal. Then it's uncoupled, and you can sort of guess that that's the case here by looking at this. So this has a point where the vectors have length 0. That will be the fixed point, and you can sort of see from these vectors what the solution, the qualitative solutions of the flow, because the solution of the differential equation is actually tangential to these vectors. So we'll be following this flow of vectors. Tangential, you think through that's if you think of the solution as a curve that in the space, then the tangent vectors of that curve is actually exactly here, this vector made from the two rates of change. So that will actually mean that the vector field reflects exactly the tangent vectors to the flow. So here is actually still uncoupled. Here is a case where one of those neurons, or both of those neurons, have gotten input. So the attractor was shifted to the right by some positive shift, and that just shifts where that attractor is from this quadrant out to the quadrant on the right, where both of these neurons would be active. So if you now want to act think about interaction, you have to take into account the sigmoid. That's only where neurons are activated would there be interaction. So here, for instance, here, any influence of neuron number 1 on the dynamics of neuron number 2 would only be present where neuron number 1 is active, so in the positive half space here. The length of these vectors would be exactly the sigmoid. And analogously, the influence of neuron number 2 on neuron number 1 would be only present where neuron number 2 is positive, so here in this half space, and it would be, again, the length would be the sigmoid. Now, inhibitory influencement always goes in the negative direction of rate of change, so towards smaller values of U1 or smaller values of U2. So if you were to add these two curves, these two vector fields, you would get a vector field that is diagonal here, pointing, towards smaller activation, and here it's just along U1, here it's just along U2. And clearly in this regime where both neurons are off, there is actually no influence from this coupling. So this is the effect of coupling. You would have to add this vector field to that convergent vector field that the inputs make. You see, they make the attractor. This one doesn't make attractors, right? This one would make actually sort of runaway solutions where you'd be running to -infinity, or here, go to -infinity. And through this convergent vector field that makes them the -u term forms, you then get again a conversion vector field. So superposing these two will lead to this kind of vector field. You can see in this quadrant, there are these strong vectors that point to negative values, and you have these relatively small conversion vectors. So these ones win, and they all just point you to the negative. Here in this quadrant, you have this strong positive vector field pushing things up. There's nothing opposing it, so that's what you will be getting here. And now here you have a slightly convergent vector field superposed with a opposing field, and that leads to some compensation and shifts the attractor into this regime. And here, by symmetry argument, you have the same kind of situation here. So you will get the same kind of arrangement here. So that will be now your bistable regime, because there are two attractors, right? And you can see now it depends on your initial condition for both U1 and U2. Anywhere below this diagonal, you would be converging to this one. And anywhere above that diagonal, you will be converging to that attractor. Now you recognize that you would be typically, if there's no input, initially you would be sitting somewhere here on the diagonal, namely in the resting state for both of those neurons, right? There will be this kind of situation. That's where you would be sitting, and then you turn on the two inputs. Oops, the two inputs, and you will be, in this case, sitting exactly on the boundary of the basin of attraction. So by chance, you would either go to one, or the other. So this would be the case where it's really, if it's symmetrical inputs and you're sitting the resting level, it would be really by chance how you make the decision. It will be, again, a case where being close to an instability gives you a chance to make decisions based on noise. Now, of course, in general, you don't have that kind of symmetric situation. For instance, you would have perhaps a little bit more input to one of those neurons, the U1, than to the other one. Like this distance here is smaller than that distance. That will be a slight competitive advantage for U1. Superposed with this, you could sort of see that that must shift things around. So here you have a more convergent vector field with the same downward trend that leads to a strong stable attractor. Here you have a less convergent vector field because the fixed point is further away, and that leads to a weaker attractor. So the boundary of the basin of attraction is attracted here to this attractor. So that makes a real difference, huge difference, right? Because if you now think of this initial condition, right? Remember again, you would be starting out here at this resting level, because when you're in the resting level, you don't know anything about interaction and input. So you would be starting out somewhere here. Now the probability to go to this attractor would be overwhelming. And it would be take a lot of noise to take you beyond this boundary here and make you attract to the other attraction. And with that level of noise, you might lose that attractor again. As soon as your noise puts you beyond this boundary, you would be reverting to the initial attractor. So that's another way of viewing these instabilities. So the decision is again made at the detection instability. Remember the decision, the selection decision, because before detection, you would be sitting in the resting state, maybe some slightly shifted resting state, but below threshold. Then you add a stimulus that gives you, let's say, the choice between two inputs, and then the vector field transforms into this vector field, and that's where the selection decision is made, for instance, in this case, to this neuron. But it's also where the detection decision is made, because it's the transition from off state here in this quadrant to an on state in one of these other quadrants. So I was going to show that in the simulator. You can go to that simulator and play with that yourself. So maybe reduce noise again, maybe to 0. Let's get rid of self-excitation. We have another button here that's the connection strength to the other neuron. So by making it negative, we can make this neuron inhibit that neuron. Nothing changed in the plots because this neuron is still sitting here at 0. Actually, I should turn the resting level to 0, the input to 0. And the second neuron, let's make it symmetric. It actually makes negative influence. It's just the exact same number, negative influence here on that first neuron. So you don't see this when they're in the resting level. Now, when I push one of those neurons up, and it would be again critical to go above 0 because of the threshold, somewhere here. Now it starts to affect this neuron, right? The sigmoidal influence makes that the slightly positive level really pushes this here to negative values. Actually, I think that shows a very large level of inhibition. Let's do less so that it's not outside the range of this plot. So as I drive this positive levels, it has more and more inhibitory influence. So now I'm at this level, let's say, I have a positive activation for neuron number 1, and now the neuron number 2 is below resting level. Right? It's really suppressed below resting level. Here's the attractor. And I can actually give now input to that other neuron. Actually, this is too much. Let's take less. To 6, let's say. Yeah. I have my 3 plus 6 that works out. So now if I go also to 6, and so now actually both of these have the same input strength, but this neuron is off and that neuron is on, above 0, below 0. So that really shows that it makes a selection decision between those two. And again, actually, this you see we're here in the rightward attractor. There's another attractor on the other end, and we're in the rightward. There is a, it's the same logic as I had before that. It was which slider I moved first. So for instance, I can remove the slider. The system switches. Now this one is on, that one's off. That's what would arise if they were both at resting level, here at this resting level, and I just turn on the second neuron first, let's say to this level of input here. So it goes to this attractor in the positive half, and then I add the second input. That's a huge time advantage because I'm doing this by hand. Think of that just happening much closer, just a little bit of a time advantage. And you see the time advantage translates into this activation advantage and turns into a competitive advantage. So now at the same level of input 6 and 6, it's the neuron number 2 that is above threshold, and neuron number 1 is below threshold. So I've shown that both solutions are stable states, and which one you get into, it depends on this difference in time. And you can, in the simulator, you cannot push both sliders to positive levels at the same time, just where you set it up, but that's something that you can program and try yourself. So you'll be invited to play with this in the exercises. Good. Yeah, and I think I want to close here. That is, I want to just point now to how we'll generalize from here. It will turn out that these two things that I just showed you, so the self-stabilization of excitatory input from self-excitation will generalize to excitation that is local among different units, and the competitive coupling that we just looked at, that we called inhibitory coupling, can be generalized to what we will call global inhibitory coupling in populations, and that will be the source of selection decisions, and that will be what happens in the neural field. The neural field will be not one, not two, but continuously many neurons. This is sort of mathematical generalization of this discrete way of thinking of neurons, and that will continue these two limit cases, because we will say that at close distances between field locations, there is excitatory coupling. This coefficient here will be positive, and at large distances between locations, there will be negative coupling, inhibitory coupling. That's shown here by this being negative. And then you will see that the fields inherit these properties. They can do selection, they can do detection, and the two combined make selection decisions in response to new input. And that will be what we'll be looking at in next lecture and much of the rest of the course. So to position that, what this field picture here will say that we'll have continuously many activation variables. And what we did so far was looking at a particular subregion that we lumped into one neuron, and another subregion we lumped into another neuron. And therefore the coupling was sort of effectively summing over all possible distances. The coupling at that distance and the self-excitation was just within each of these regions. But more generally, it would be a question really of distance in a representation like that, that will determine what the effective coupling strength is between different units. And so that's what we'll be elaborating in the next couple of lectures. So this is how I want to end this first brush, or this first contact with neural dynamics, and we'll be open to discuss with you.